Question 26 is about two charges with 2 times 10 to the minus 19 coulombs on them. Move that up here. So they're 2 times and 2 times 10 to the minus 19. And it says they're 3 meters apart. Okay. It's saying it wants the electric force on Q2 and the electric field due to Q1 at the position of Q2. Okay, so in order to find the force, we go there. K in your data booklet is 8.99 times 10 to the 9. So I'm going to go with 9 times 10 to the 9 times by 2 times 2 10 to the minus 18. Okay. Divided by 9. So if I cross out the 9's, and then 9 minus 18 is minus 9. So the final force is 10 to the minus 9 newtons. So it's either A or C. Then we want the electric field. So the electric field is force divided by charge. You could do it with kq over r squared. That's another alternative. So I'm going to go with force divided by charge. So we've got 4. Sorry. Lost the screen. Bear with me a sec. So the force is what we just found out, 4 nano newtons divided by the charge, which is 2 nano coulombs. The nano drops out. 4 divided by 2 is 2. So it's this one or this one. So it's A. Question 27 is looking at resistivity. So we're looking at the resistivity equation. And we're trying to find out the ratio of the resistances of X to Y. So resistance is rho L over A. So Rx is the resistivity of X, which is rho, multiplied by the length, it has a length L, divided by the cross-sectional area, which is pi r squared. So we've got D, so it's pi d over 2 all squared. Okay, so what we end up with is rho L over pi d squared over 4. So we end up with 4 rho L over pi d squared. So what you can do when you've got a divide by a divide, the 4 can jump up to the top. So that's Rx. Next we find Ry. And we've got resistivity, so it's RL over A again. Resistivity over 2 times by 2L times by d over 2 all squared. So that's going to be d over 2 is the diameter. So we're going to divide that by 2 to get the radius and then square it. So let's just cross out those 2's. They can cross out. So we end up with d over 4 all squared. So that's d over 16 squared. So we end up with 16 rho L over pi d squared. Apologies, I forgot the pi there. Okay, so let's cross out the pi's because they're constants. We don't need them. And we can cross out the rho L d squared, rho L d squared. So we have Rx is proportional to 4 and Ry is proportional to 16. So Rx to Ry, 4 over 16 is 1 over 4, which is 0.25. So D. Question 28 is about the electric field between parallel plates. Apologies, gravitational field. Gravitational field between parallel plates. Okay, so the potential difference between the plates is adjusted until the particle is held at rest relative to the plates. What change will cause the particle to accelerate downwards relative to the plates? Okay, so if we've got a negative charge in the middle of an electric field and we want it to move downwards, we want it to move away from the positive. So we want it to move away. So we want it to be less attracted to the positive plate. So the only way to do that is by making the charge smaller. So we make it less negative. If it's less negative, it will be less attracted to the positive plate. So can we do that? Yes, we can. A, decreasing the charge on the particle. It's going to become less attracted to the positive plate, and then it's going to be accelerated down towards the ground. Okay. 29, we've got a potential divider. The resistance of component X decreases. So we've got 2 resistors, and it looks like the X is an LDR. What is the change in the reading on the ammeter and the change in the reading on the voltmeter when the light incident on X is increased? Okay, so when you have an LDR, if you increase the light, so we've got light increase, the resistance across that resistor decreases and the current in the circuit increases. Okay, so first of all, if we're increasing the light, I know for a fact the current in my circuit is going to increase. So it's one of these. And then in a potential divider, how it works is the ratio of the resistances is equal to the ratio of the voltmeters. Okay, so in other words, let's call that Y and this one X. Yeah, Rx to Ry equals Vx to Vy. So if my resistance in X is dropping, the voltage in X will drop by the same proportion. So the voltmeter is going to decrease. So the answer is A. And then question 30, I can't show you what I'm doing, but I'm currently doing the Fleming's left-hand rule here. We've got a particle of mass m and charge of magnitude q entering a region of uniform magnetic field that is directed into the page. Okay, so the B field is directed into the page. That's how I'm going to draw it. The particle follows a circular path of radius r. So here's the radius r. What are the sign of the charge and the speed of the particle? Okay, so let's look at the sign first, the sign of the charge. So we need Fleming's left-hand rule. So this is the current, this is the particle. So we've got a particle here. It's positive or negative, we're not sure yet, but the charged particle is moving in this direction. Okay, and we can see that the force that's causing it to go in a circular kind of centripetal force, is acting downwards at this point, which is the point where they're interested in. Okay, here. So the force is acting downwards. I'll just clear that up for you so you can see it really clearly. Okay. So with Fleming's left-hand rule, we've got the force acting downwards. So your thumb is acting downwards. And your field, your first finger field, is acting away from you into the page. All right, into the desk, however you're holding the page. Okay. Now, for that to happen, you must have your finger, your second finger, your current is going backwards. It's going from right to left. So what that means is my second finger is saying that the current is going that direction. Okay, so if it was a positive charge, it would be going right to left, to the left of the page. However, it's clearly going left to right. It's going in this direction, so it's the opposite of positive. It's a negative particle. So it's one of these. And then to find the speed of the particle, when we've got centripetal motion in a magnetic field, what we have to do is we have to equate the centripetal force to the magnetic force. So V is the speed, and so we can cancel one of those out automatically. And we're trying to rearrange for the speed. So I'm going to bring up the R and take over divide by M. So I end up with V, equals BQ R over M. They've used a capital R, I've used a little r, but yeah. Okay, let me just correct that so that we're using the same notation. So it's B.